Welcome to Weather Extra on CBS News Bay Area. I'm KPIX5 meteorologist Paul Hagan. Usually, we take a closer look at a weather topic, a deeper dive than what we can do within our daily weathercasts on KPIX. But this time around, this isn't a weather extra segment at all. Instead, it's space extra, because on July 12th, NASA released the much anticipated first batch of images from the James Webb Space Telescope. I'm going to go through those images one by one, give you some perspective as to why they're important. But first, a little bit of background. The James Webb Space Telescope is a project that started with scientists knowing they needed a telescope to follow up on discoveries made by the Hubble telescope. So in the mid-90s, the idea of an infrared telescope with a large mirror was formally proposed and approved. Over the next quarter century, the project slowly came together and the telescope was finally launched on Christmas Day 2021. The last 6+ months have been spent getting the telescope into position, making sure the component mirrors that make up the telescope itself are aligned perfectly, and finally in gathering this initial batch of data. Webb is an infrared telescope, meaning it's designed to see light with wavelengths longer than our eyes can see. This is important for astronomy. Warm objects emit infrared light, everything from the dust that's scattered between stars to planets, stars, and entire galaxies. With Webb, we'll get a better view than we could ever get with an optical telescope, the kind you usually think of when you hear the word telescope. Beyond that, an infrared telescope will give us the best data yet on distant galaxies at the edge of the observable universe. The Webb telescope has a battery of filters that converts the infrared data into color images. They're pretty to look at, but they also tell us a lot about how the universe works. Let's start with an image of the Southern Ring Nebula. This was Hubble's view, while this is the image from the Webb telescope. It's a planetary nebula, which occurs when the star at its heart expands into a red giant and then ejects the outer material away after it runs out of fuel in its core and essentially dies. This will happen to our own sun over the next 5 billion years or so. The remnant of that star is a white dwarf, which then blows hotter and faster gas out into that outer layer of debris. That carves an expanding bubble into the outer layer, giving the nebula its distinctive look. What's unique about this new view is revealed by looking at a different part of the infrared spectrum. The star at its center is actually two stars, a binary system. The other star is buried in so much material, it's not visible in the shorter wavelengths. These images will help astronomers understand how stars like our sun behave at the end of their life cycle and help astronomers understand how binary star systems work in the first place. Next up is the Carina Nebula. Once again, Hubble's view versus the Webb telescope. This feature is about 7,000 light years from Earth, and it's one of the Milky Way's most active stellar nurseries. Stars form in clouds of dust like this. Gravity draws impossibly small pieces of material together continuously over the course of millions of years until so much of that material is packed together that it ignites as a newborn star. In this image, you can see several very bright stars at the top of the image. These are massive stars, sending out radiation and solar winds that eat away at the gas and dust of the nebula, leaving behind a wall of material that's this brightly, sharply defined line with dense material remaining in the cloud. Again, looking at a different part of the infrared spectrum, we can see the effects of that shock wave. Even more stars are being born within the cloud. Some starting to clear away that dust, others still kind of shrouded, surrounded by the very materials that help them form. So why is this important? Astronomers already understand a lot about how stars form, but there's always more to learn. High-resolution images like these will help them see the entire process more clearly. An analysis of each individual star will tell us more about how stars first ignite, what happens to the material around them when that happens, and how some of the leftover material will form planets around those stars. So let's move on to Stephan's Quintet, a cluster of 5 galaxies. At least it looks that way. This one on the left is actually a galaxy that is much closer to us than the other 4. So there's an optical illusion at play here. The other 4 galaxies are actually interacting with each other. These middle 2 galaxies are well into the process of colliding. Something that happens more often than you'd think. Our own Milky Way galaxy will collide with the Andromeda galaxy in about 1 billion years. The gravity of the 2 galaxies send out streamers of material called tidal tails, which will cool and form new stars. Switching into that alternate infrared view, look at the galaxy at the top of the image. The center of it is very bright, which means we're seeing the enormous energy emitted by a supermassive black hole. There's one of those at the center of every galaxy. This one obviously is in an active phase of its life cycle. The data from images like this can give researchers A wealth of new information, how massive the black hole is, how much material it's consuming, what happens to that matter as it crosses the event horizon, and how some of it is actually blasted away from the black hole at speeds approaching the speed of light. All that stuff is really cool, but the next image is the one that's really mind-blowing. This is the first deep field image from the Webb telescope, where it looks into the space in between visible stars to capture dimmer, distant stars and galaxies. There is a lot going on in this picture. All of the stars with spikes emanating from them, those are stars within our own Milky Way galaxy. We can actually ignore those for now. At the center of the image is a galaxy cluster, a collection of hundreds of galaxies, at least, orbiting a mutual center of gravity. This one's about 4.5 billion light years from Earth, which means the light we're seeing in this picture was originally emitted when the Earth was only a baby planet, only 100 million years old, maybe. The whitish circular blobs are part of the cluster, but you can also see dozens of irregularly shaped galaxies that kind of look like they're curved into arcs or almost smeared out. Those are far more distant galaxies, well beyond the cluster as seen from Earth. We're seeing those distant galaxies because the combined mass of the galaxies in the cluster warps the light coming from the objects behind it, a process called gravitational lensing. The lensing makes them look like arcs, but then the gravity of the individual galaxies in the cluster piles on, further bending and distorting the shape, so some really don't even look like galaxies as we typically think of them. The great part, though, is that the lensing effect also magnifies and amplifies the light from those more distant galaxies. They might be too dim to see otherwise. So we're getting a look at phenomena that would ordinarily be too far away for us to normally observe. There's plenty more in this picture, background galaxies that are unrelated to the cluster at the center. But we're going to really zoom in on this image. You can do the same. There's a link in a tweet that's pinned to my profile. So we start with a similar perspective, but zooming in on one of the white blobs at the edge kind of looks familiar. That's an entire spiral galaxy, actually a couple of them, similar to the Milky Way. There are so many of these in that deep field picture, it's almost overwhelming. There are over 1,000 different galaxies in the deep field image. Each galaxy contains roughly 100 billion stars. But let's zoom all the way out to the full sky perspective. It's going to look like the deep field image completely disappears. It's still there, but the zoomed out view shows what a tiny fraction of the sky we're looking at. All those thousands of galaxies are in a piece of sky so small it's the same size as a grain of sand held out at arm's length. Well, all these galaxies are eye-catching. The ones that astronomers are most interested in are actually the faintest ones, the tiny little red dots. Those are the most distant ones, dating back to the universe's first billion years or so. Understanding how the universe was behaving then will be one of the biggest contributions the Webb telescope makes to our scientific knowledge. So how far away are those red blobs? The Webb telescope took spectra of some of them, breaking their light up into individual infrared colors. Astronomers analyzed those spectra to find the distance to the galaxy and what elements are in it. The more a galaxy's light is red-shifted on the infrared spectrum, the farther away it is. The faintest ones date back to just 700 million years after the Big Bang, that faint little red dot right there. One more bit of data. This one is especially interesting to me as an atmospheric scientist. This is an artist's rendering of WASP 96b, a Jupiter-sized planet orbiting a sun-like star about 1,100 light years from Earth. This planet is nothing like Earth. The top of its atmosphere is about 1,000 degrees Celsius. It whirls around its star every 3.5 days. But the fact that it has an atmosphere is interesting, and we want to know what it's made of. This particular planet's atmosphere doesn't have much cloud cover, and the planet's orbit takes it between its star and our view from Earth, what's called a transit. So the light from the star passes through the planet's upper atmosphere on the way to Earth. The atoms and molecules in the atmosphere absorb very specific wavelengths of that light. The spectrum of the light reaches us, shows little dips and spikes in the light absorption caused by the stuff that makes up that planet's atmosphere. That reveals its composition. The spectrum reveals the presence of water vapor in the planet's atmosphere. The spikes in the spectrum are where steam absorbs infrared light. Not only does it show that it's there, but it also reveals how much water vapor is there. The surprising thing is these readings don't quite match the computer models of a completely cloud-free atmosphere, meaning there are some clouds in the sky of WASP 96b, it needs a better name, as well as some haze. This isn't the first spectrum of an exoplanet's atmosphere that we've seen, but this one is important because of its level of detail. Other spectra of other planets' atmospheres will reveal more information, like the presence of organic molecules, such as methane, that would indicate the possibility of life. This process should also work with smaller, more Earth-like planets, although it's more difficult because those atmospheres are generally shallower and more challenging to sample. But it's so exciting that future observations could reveal what's happening in the atmospheres of planets like ours, orbiting stars trillions and trillions of miles away. That's it for this week's Weather Extra. Meteorologist Darren Peck will be back next week to cover another topic, one that will return to Earth's atmosphere. And we're always looking for new ideas for these segments. If you have a weather or climate question, just email it to weatherextra@kpix.cbs.com.